So if you have any issues with the connection, let me know. It should be okay still. Okay, so I chose to today talk about the journey in my group that led to the work that we are doing now, because I thought that it could be helpful for, let's say, young academics to figure out what the logic was in choosing the research topics in order to come up with the group that I'm now leading at the University of Luxembourg. So I will show you some basic results, but most importantly, I will try to be as clear as possible about how I decided to go in a certain direction and why I did not go in another direction over the years. And then once I'm done with that, I would also like to give you a bit more detail, and that will be probably in the second part, about mesh-free methods, partition of unity methods, and extended finite element methods, and a bit about material point methods, because we just released 2 books, one on the material point method and one on partition of unity methods, with Nguyen Vinh Phu for material point methods, and with Sundararajan Natarajan on XFEM and partition of unity methods. So Phu is my first master student from 2003, and Sundar is my first PhD student from 2006. So that's why these 2 books for me are very important, because they were done with people that are very important to me, mainly my master's and PhD student, the first ones. So the first ones are always the most important. So, okay, let's see how we got to where we are now. So it's the title is Data-Driven Journey, because I realized without knowing it a priori how I got about building the logic in my research that I'm now leading at the University of Luxembourg. So I'm going to try to explain this to you, and feel free to ask questions if you have any. At the beginning, I started my PhD on topics that were related to aerospace engineering, and I was working on a Boeing 757 engineering electric access door, which is a piece of aluminum. And the question there was the durability in terms of fatigue life of this component. So we were interested in figuring out how many takeoffs and landing the aircraft could go through before we would need to actually repair the aircraft, or at least inspect the aircraft to figure out if cracks had propagated. And at the time, we were not yet talking about composites. This was before problems like the Airbus A380 and new designs of components based on composite materials, which you see here. So it was mainly aluminum, and we were interested in the propagation of a crack. And the crack was assumed to be pre-existing in the structure. We were not able to initiate the cracks. We were only looking at propagation according to damage tolerance design analysis, which is what the Federal Aviation Administration is doing in the US. So this is basically the beginning of my PhD, and I'll come back to how it got completely transformed thanks to my advisor, Brian Moran, who gave me the opportunity to work in bioengineering, in particular on biofilms, which was a topic originally I thought was completely different from fracture, but in fact, I realized was in fact very close in terms of mathematical modeling. And this is something that really is pervasive in the work that we've done over the years, is that we tried to identify the common denominators between different applications and try to formalize them at a level of abstraction which is independent of the application, so that if we can make some progress at the abstract level, we can have implications on a series of applications. So this is what you see below here, the surgical simulation part of the slide, which started roughly in 2006 when I started my first academic position. So I was 3 years after my PhD. And I went to Glasgow, University of Glasgow, not far from Strathclyde, actually. And I worked there with Chris Pierce and Nenad Bicenic, whom I would like to thank, because they were very supportive and helped me a lot in learning to write proposals, for example. And so what I decided at the time, completely by accident, I met a neurosurgeon, and this neurosurgeon told me that they would really benefit from having a way to simulate different operations in order to predict the outcome of the operation. So you can imagine, I will give you details in another presentation, but on the biomechanics of the brain, but for now it's enough to know that the brain is a deformable structure which is porous, at least there is some debate about this, but let's assume that it's a sponge, and that this sponge is going to essentially lose the water that's inside the sponge during the operation, so it will shrink, and this shrinking process makes it difficult to predict where the tumor is going to deform during the operation. You imagine craniotomy, so you make a hole in the skull, the cerebrospinal fluid leaks out of the brain, and your question is, how should I either insert an electrode or remove the tumor, because everything is moving, and in order to have real-time imaging on a real person in the operating theater, it is still quite costly and long, which is not good because you keep the patient on the table for too long. So the idea would be to try to accelerate these, and also to help surgeons train on virtual simulators of surgery in order to decrease the cost to the medical system. And so how did we think about this? Well, basically, in the first case at the top, I was working on fractures, so on cracks, and at the bottom case, we were talking about cuts. So essentially trying to figure out how to cut an organ and what would be the resulting discontinuity. So as you can see here, there is a cut by a scalpel and it creates a discontinuity, similar to what you see here with a crack or a delamination, which creates also a discontinuity. So the question that we really started to wonder about is, how do we reduce the problem size? Because for surgical simulation, you cannot wait for 1 week to get a result. You need to get the results in 1 millisecond. But we need to control the error in the quantity of interest. So I will come back to what that means later in a different talk. And then how can we do that for realistic problems, for large multi-scale mechanics problems? So that was really the overall encompassing idea. And what I have to say about this is that in 2006, I was very naive about our ability to do this in a constructive way and in a positive way. I was very, very naive about the time it would take. I thought that maybe in 5 years we would be done. I was lucky enough to get an ERC grant for a substantial amount of funding from the European Commission, which was very competitive. But even with this amount of funding, in 5 years, we had really only scratched the surface of the problem. So this is also something for younger academics that can be helpful to know, is that it's, in my opinion, very useful to have a grand idea, because even though you don't reach the goal itself, it allows you, this vision, to go and to move in a direction which is competitive and helpful to the community. I think it's very important not to be too shy and to try to take risks, especially early on in your career. So I could come back to that later on how to handle this in a practical way. So let's start by what happened during my PhD. I'd like to start from basics. It's always helpful to know where people come from. So you see here, what I've done is I drew a graph which has time on the horizontal axis and data on the vertical axis. And this curve here is an approximate representation of what I believe were the amounts of data versus time. So at the beginning, during my PhD, Northwestern, 2003, we basically had to rely on models which were a priori written in stone. So for example, we were working with Paris law, as you will see. We were looking at the propagation of fractures in aerospace components that are made of aluminum. So we just looked at the literature, and of course Paris law is the most well-known approach to do that. And this is a semi-empirical law. which essentially looks at observations and tries to decide what to do with these observations. What would be the rate of growth of the crack as a function of the number of cycles? And this is exactly what you're interested in, because you would like to know between flight 1 and flight 10,000 how much, so the how much growth did the crack go through. So here the vertical axis is giving you the speed at which the cracks are growing, n is the number of cycles, so of flights, and dA is the increment in crack growth. And on the x-axis you have the stress intensity factor, which you can compute using domain integrals. We can come back to that if you're interested. And basically what you do is quite trivial, is you compute the stress intensity factor. It's not easy, but it's, it's conceptually simple. And you then, based on the stress intensity factor, deduce the amount of crack growth, which is proportional to the number of cycles. So dA equals dN times delta K to some power. And the power is again an empirical factor, and you have some sort of proportionality coefficient, which is again an empirical factor. So as you can see, you have a lot of data hidden in this Paris law, because people did thousands of experiments. But in a way, we are not using the data ourselves. We're just using the fact that people derived mechanistic laws, mechanistic systems, mechanistic methods and models. I could come back to what mathematical modeling is, but I didn't want to do that because of the audience, which is experts in the domain. But sometimes it's worth thinking what we mean by modeling, because everybody uses the word model in a different way. So here what we're doing is we have a model. The model is the Paris law. The Paris law contains experiments, but we do not do experiments. I did not take a piece of aluminum, and I did not subject it to fatigue load. Other people did that over the years, and when I did my PhD, it was approximately 40 years after the initial Paris paper and with Erdogan, and that led us to a way to compute. So that's what I started with. After that, the first thing that I started to work on was a nonlinear fracture, because fracture mechanics in the terms of linear elastic fracture mechanics makes quite a few assumptions, and sometimes these assumptions don't hold. For example, if you're looking at the fracture of a pipe under ductile conditions, this was the work that we did with Timon Rapsuk, and Timon is a great friend and also a great professor that you probably know. He's now in Weimar, and he's been for many years. Now vice president for research in Weimar, and he introduced me to nonlinear fracture because I didn't know anything about nonlinear problems, and so we discussed and we worked together on mesh-free methods in that case. And again here, what did we use in terms of model? Well, we use this model here. I mean, we use many others, but for example, this is an example of model. This is called von Mises plasticity. You have also Tresca. Yield surfaces and so on. This is used a lot in soil, but also in metals. Tresca is used in soil in particular. And I used that during my master's on geotechnical engineering. So basically what we see here is that you have, again, a mechanistic model. So you have a phenomenological model. Someone says, okay, we assume that plastic deformation does not depend on pressure. So whatever the pressure is, the plastic deformation will be the same. So that's basically an assumption. Right? So if we have the hydrostatic axis where all three components of the stress tensor on the diagonal are equal, well, then we say that depending on the pressure, which is the sum of these three diagonal components, well, depending on that, we will have always the same plastic behavior. And this is an assumption. But of course, there are many, many other ways that we could do this. And we are now, again, assuming the material is behaving as an homogeneous material. But von Mises plasticity assumes that at the lower scales, there is some sort of coalescence of voids. This is what von Mises plasticity assumes. So there is a mechanistic understanding of what goes on below the scales, at the lower scales. But again here, we are not modeling the whole structure, including the voids that are growing and coalescing. We are only interested in the macroscopic behavior, which includes the mechanistic understanding of the smaller scales. So that was the second thing that I worked on. And I just said void nucleation is not taken into account explicitly. We just use the model as is, out of the box, Someone wrote the model down, we use it, that's it. So I think it's a very important concept because the whole paradigm these days is changing very rapidly towards a direction where you in fact are using real-time data as you acquire it. So we will come back to that in another lecture, but I just want to say that the logic behind this is that we move away from mechanistic understanding to actual observation of the system. So instead of having like what we have here in the Paris case on the bottom left, where you essentially look at a system in terms of what other people looked at over the years, and they gathered a lot of data about many systems that look like your system. Today, what you are able to do is you are actually able to use the actual data on the actual system that you are interested in. So as if for the Boeing 757 EE access door, I could have actually modeled the door that was in my office, in fact, that was very heavy. And this door, I could have modeled that particular door. So this is where we are going now, and this is what people call digital twins. And we will come back to what that actually means, because this is also very old, 50 years roughly, invented by NASA. So once we were done, we are never done, but once we moved away from von Mises plasticity and nonlinear fracture, well, what I decided to do is to try to see what was going on in the smaller scales. And that happened because I started to work with Pierre Kerfrieden, who is now at École des Mines de Paris in Paris. And he was one of my most influential collaborators and taught me so many things about multiscale fracture and how to write these fracture models in a variational form, as well as Lars Beek, who is now in Luxembourg in my team as well, who taught me a lot about the quasi-continuum method. So essentially what we did here is we tried to figure out, okay, now we do know the macrostructure. We do not want to rely only on what other people did in the past. We would like to look at the actual macrostructure of what we are dealing with today. And that motivation, in fact, was not at all from materials like steel and ceramics and so on. It was more from the biomechanics angle that I told you about before. Because when you have a patient in front of you, you may have made many experiments on other patients in the past. First of all, these patients were most likely dead because it's not possible to make experiments on living people. So the values are all wrong. On top of that, you have very few patients to look at. So you have a lot of missing data, a lot of missing information. So that's why, contrary to engineering materials like steel or aluminum, where you can just use millions of samples, and you can hope to have even more samples with time going, with, let's say, cases associated with the human body, things are very, very different. And we submitted on this a paper to proceedings of the National Academy of Sciences yesterday on the knee meniscus, which I hope will be accepted because it's very exciting, with Anna Sobeidat and our colleagues in Oxford, Olga Barrera. So why do we look at microstructures? So the question is that each material is different, right? So, and more than that, each structure is different. Maybe it's made of the same material, but if you look closely, you will see that the grains that you have in this material, for example, if it's a ceramic or if it's a polycrystal, doesn't matter what it is, these grains will be different. So we have a project at the moment working on space science, where we try with a startup in Luxembourg to come up with a new alloy which will be able to shield from radiation some spacecraft and astronauts, as well as the electronic devices on the spacecraft, because they are fried by the cosmic rays. So what we're trying to do is to come up with a new microstructure. So in that case, we don't know the microstructure even. But even if you do know it, if you take another piece of material, I take, this piece of material, I look at it with a microscope, I will see some sort of grains. If I take another one, I will see other grains. Of course, there will be some statistical distribution, which I can use, but each material will be different. And each point in the material will be different too, right? So the idea is, how can we take that into account? So that was the next step in our journey. And in that case, of course, we need more data, because how do you come up with this microstructure. I will have a whole lecture on multi-scale fracture and model order reduction, so we can discuss that in detail at that time. But what's important to realize is that we have now more data, of course, because we need to come up with a so-called representative volume element, which is this little box that you see here, the little square that you have here, and which is supposed to be representative of the higher scales in the domain. So that's basically what you're trying to do. Okay, so that we are moving slowly along the data axis, so we are, increasing in terms of data. And then when things became totally out of control in terms of data acquisition was for biomechanics, because what you see here is, well, basically a tumor in a brain. These things are very nasty. We have now a few people in the group, in particular Miriam and Stéphane Urquin, and Thomas Lavigne and others that are working in this area of trying to predict the growth of glioblastoma and the malignant transformation of cancerous, let's say of non-cancerous cells into cancerous cells. And so I could give also a lecture on that later if you're interested, because it's quite an exciting topic, and that can have quite an impact on actual people. So what you see here is a tumor, and of course the problem is, as I said before, that if you open up one person, it's always different from any other person. You don't have the same people, right? So everybody is different. That's very, very clear. Even if you open up identical twins, they will not be identical. Things are very different. So what do? You need to acquire data. And in the case of the brain, as you can see from this picture, the brain is a very intricate organ. It's got quite a number of sulci, which are these little folds in the brain here that you can see. And they are made of they contain neurons, they contain glial cells, which are cells that we thought for a long time were useless, but in fact hold the neurons together and also help with garbage collection from the neurons. They also help to bring metabolites to the neurons so that they can actually function. So all these cells are very important. And the question is, okay, what do we need to model in this? It's such a mess. There are things everywhere. It's very complex. There is fluid in it. There are some pores. Fluid is maybe even flowing. There are some debates about this, how it flows, or if it flows in and out of cells, or if it's only surrounding the cells. So there are lots of open questions, but still it's a problem which is really not easy to model. So what do we do? Well, we need more data, that's for sure. And that's what the thesis of Stéphane Urquin in the team was about, is trying to figure out what model can you use? Because now the question is, what are you interested in? If I'm interested in figuring out whether that person has Alzheimer's disease, I will be interested in looking at very specific data about the neurons. For example, if there is plaque on the neurons or not. If I'm interested in doing deep brain stimulation for Parkinson's, to avoid shaking, then I'm interested in a completely different topic, which is the electroconductance of the brain tissue, because I need to know where to put the electrode, and I need to know what distance, I need to know what pulse, and so on. If I'm interested in removing a tumor, maybe I'm interested in the stiffness of the material and how it will contract when the water comes out. So there are many, many ways to look at the brain, and we're not always interested in everything. But so our question was, okay, how do we actually get data? And so because it was very hard, we started without data. So we started only with very, very basic MRI of one patient, and our idea was to solve the problem in real time. That was the novelty. So this is something where we pioneered the use of error estimates, which is also something I would like to talk to you about, maybe not this month, but maybe at a future colloquium that we could organize, or future short course, where we could invite also some colleagues that are experts in error estimates from the applied math community, where the question is, how do you actually control the discretization error once you know that you're solving the right problem? And we could come back to that also, because I think it's a very, very important point that many confuse. right? So here what we did is we did not wonder whether the model was correct. We said, okay, the material model is extremely simple. We will say it's co-rotational elasticity, which means that there is only some sort of geometrical nonlinearity, but there is nothing in terms of material nonlinearity. Everything is linear. So extremely simple model. And the parameters we just guessed. So again, completely simple and deterministic in the sense that we don't have any of those, probabilistic distributions for each parameter. We just assume they are fixed, constant, and known. So problem solved, very simple. Okay. So that assumes that the problem is known, so what material model is going to be used, but we don't know whether we solve the problem correctly. So we assume we solve the right problem, big assumption, but we don't know whether this right problem is solved right. Is it solved correctly? Is it accurate enough? And for surgical simulation, it would be nice to be able to tell the user that the error is less than, let's say, 5%, because you want to know the accuracy at which you get the position of the target, for example. So therefore, this is where we went, because I remember very clearly in 2006 when I wrote that first ERC grant, I said I will never look at constitutive models. I will never look at material models because I don't want to know what the material is doing. This is not my field. There are some experts like Ogden, Holzapfel and others, Gasser, that are really, really experts in modeling large deformations. And I didn't want to work on that. Recently, we've completely changed this idea because we realized that without working on the models, we would never be able to do anything patient-specific, So we said, okay, well, we will need to look at the models. And essentially, we went in the direction of Giuseppe Sciume, who worked and pioneered the work on porous material models for soft tissues. And so that was a really big step in that direction with Stéphane Urquin's PhD thesis. So now the question is, what can we know about the material model? Because the big question is, as we said, all humans are different. So if they are different, how do we know what material model to use, and how do we know what material parameters to use? So that was really the problem. So because we don't know that, we assumed that we have a probability distribution for each of the important parameters. It's not very important to know which parameters at the moment. Let's assume there are two parameters, C1 and C2, and we have random fields. So now we look at the brain, and the brain now has different colors. The colors correspond to the value of the parameter. So maybe here the parameter is higher, here it's lower, and so on. And so the question is, okay, what are these values? And we then take some different realizations and we perform what's called Monte Carlo analysis, and we try to see the impact on the position of the target. You see, so this is the deformation of the brain during surgery, and you have the initial point and the deformed point, so you see that there is some motion. And the question is, how accurate is this simulation, right? So can we predict the error? And what is the confidence interval that we have? So you can imagine that the sphere will deform and it will move. But of course, we don't know how much it will move. All we know is that it will move. And so the question is here is, what is the confidence interval? What is the 95 confidence interval, which tells us that we have 95% probability that this target moves in that area? Right, so now we cannot say for certain. We are not deterministic anymore. Now the simulations are stochastic. They are, and this is very important to realize because they are not deterministic anymore. Okay, so yeah, so essentially that's what we moved into. So now we started saying, okay, no material model because it's not my field. Finally, I said, okay, now maybe material models, but we keep the model, but we change the parameters. And we derived some approaches with Paul Ozeux and Jack Hale on how to sample the parameter space let's say, in a better way, so that the calculations in Monte Carlo are faster, because as you can imagine, these calculations are very slow. You need tens of thousands of forward simulations to be able to predict the confidence intervals. And that, of course, is not very practical if you want to solve problems which are associated with surgery, because surgery is something that needs to be done fast, as we said before. Okay, so now we increased the amount of data, and now what are we looking at here? You could probably take a guess, and I'm sure you'd be right, that this is a porous material. This is work that we did and still are doing with Olga Barrera in Oxford. And we are moving through a piece of material, and this piece of material is, as you can imagine, taking quite some time to gather information about. So now we are following one of the little channels inside this material, which is really quite impressive. And that material is actually located in your knee. This is the little cushion that absorbs the shock between your femur and the joint. So essentially this is known as the knee meniscus. It's a crescent shape, and it is thought to be used for shock absorption, so energy absorption in the body. And this is how the microstructure looks like. And the paper we submitted yesterday to PNAS, to PNAS, is on unraveling the logic behind this microstructure to know what were the characteristics of that microstructure that creates the energy absorption mechanism. I could present this paper at some other time if you're interested. It could easily take an hour because it's a very, very interesting problem. And I think it's one of the best work we've ever done with Olga, Anas, and Stéphane Urquin, and other students in my team, such as Camilo, for example, and Mardi, because it was really the first time that we were able to look at actual data. So we are high on data range now. Use that, generate some, let's say, synthetic microstructures, and try to figure out what, by solving CFD, so Navier-Stokes equations in that meniscus, trying to figure out what was the logic behind the behavior of the tissue, right? So this is what you see here. The meniscus is this little thing that you have here between the two bones. And if you don't have it anymore, then it just is extremely painful. So if you do long distance running, as Elena Troshenko is doing, or as I'm doing, maybe some of you are doing too, then you see that these things are very, can wear out. And if they wear out, then you have a problem, because you have bone against bone, or cartilage against bone, or cartilage against cartilage, but this is very painful and not nice. So the idea is, how can we try to replicate a knee meniscus, which is as good as the original, but a little different, let's put it that way. Because we don't want to copy paste, because it's so complicated. As you saw the microstructure, we cannot just 3D print this, because it's nanoporous, so the pores are nanoscopic size. It's not possible to copy paste using some 3D printing, so we need to be a bit smart about it. So this is how it looks, and we really are now working on the modeling using CFD, and we submitted the PNAS paper yesterday on that topic. So this is what you see here. We just took the microstructure and solved the CFD problem, but it's not just take the microstructure. The work to be done for this is huge, and so we use the particle method in order to solve the problem. So we use the mesh-free methods based on essentially discrete correction of particle strength exchange, DCPSE, which is a way to compute the interaction functions between the different particles. So that's it. And the idea would be to manufacture and test artificial menisci, and to then make that happen. So this is really what Olga Barrera in Oxford is interested in. And we worked a lot with her on the modeling and the simulations. And here comes the problem of data, of lacking data, because we, as you can imagine, we do not have hundreds of samples of menisci. So we have one model. This is the model of the meniscus that we are working on. But it could be that at different points, the behavior is different, right? So maybe here it's isotropic, here it's more in that direction, or here it's anisotropic in that direction, and so on. So depending where you are, you do not know for sure what the behavior is, but you don't have enough data on this particular meniscus. In fact, you have no data at all because you never saw the meniscus before. And so what you'd like to do is to merge data from different menisci that are taken from different individuals and then map this back to one specific model of the meniscus. So I think that's quite a smart idea that we worked on, and it's working very well. Okay, so then where are we going from there? Because so we have now many projects that are essentially only data. So, you know, so I'm not talking about everything. We have a very nice project with Jakub Lenkiewicz and Alexander Tkachenko in physics on the quantum continuum coupling. So we are looking at delamination using van der Waals interactions and proving that van der Waals interactions are really essential in figuring out the, well, simply the interactions between two layers of atoms, and that they see each other up to micrometers and not nanometers, as pairwise potentials would indicate. So if you're interested in this, we could also discuss it. But now what we're working on is cases where we have a lot of data, but we have very little knowledge about the system, you know? So this is now where I think the whole world is going to go, which is essentially the direction where the data acquisition is easy. We have a lot of Internet of Things, we have sensors, we have lots of things we can rely on, and these things are giving you data very fast. So very fast data flow, and this is absolutely mind-boggling, but the problem is we have no understanding a priori, as we did here for fracture mechanics. You know, we had Paris law because lots of data had been acquired. Now we're looking at systems that we don't know. We are acquiring data, and we are trying to use the data in real time to update the model of the system to then make good decisions about the system we are interested in. So that is, I think, the major change in paradigm that is taking place in computational methods. So we are not anymore interested in fixing the problem, solving. Now we are solving on a system which is evolving over time. And that system is giving us data about itself as it is living its own life. And this is what people call digital twins. Because then you have a virtual replica of the system in your computer. And the nice thing about that is that you can ask questions to this system, and the system will tell you what to do. So that's at least the general idea. And we have even cases that are led in my team by Eleni Koronaki and Anina, as well, Sarkic Glumak, that are Marie Curie fellows, and what they saw is that they can actually rely on data only. So for example, we are working with a company in chemical engineering where there is a priori no model, there is only data, and we try to glean information from the data in order to lead the model to fruition. So to guess what the model is or update the model parameters, and this is going extremely well. It's very exciting. I could talk about that too at some point, and also about wind energy harvesting in cities. This is what Anina is working on, and she's working on trying to put wind turbines in cities in an optimal way by measuring wind velocities in real time and trying to update the knowledge that we have. So it's a mixture of wind tunnels with actual CFD, with fluid structure interaction, and it's an exceptionally exciting project that can also actually handle pollution. So this is very, very cool. Okay, so now that we have talked about the basics of where the data is, I just want to give you a few hints as to one particular example in the brain. So this is what you see here. This is now something where we have data, but the data is very, very difficult to access. This is data from an astrocyte in a mouse, And what is an astrocyte? So an astrocyte is one of the glial cells around the neurons, and these cells are here, and I will come back to it, to be able to do a lot of things. They are providing food to the neurons, they are taking garbage out, they are keeping the neurons together structurally, so they are really helpful to secure the structure of the brain. But as you can see on these astrocytes, that's one astrocyte, and it's got lots of feet everywhere, lots of ramifications, lots of very small things. It looks really like a galaxy. That's why it's called astrocyte. And when you think about that, you're thinking, well, it's very difficult to model this. So you would like to solve advection, diffusion, convection, reaction, diffusion in these astrocytes, but look at the complexity. So we want to basically build a mesh of this. It's completely mind-boggling. And so Sofia Farina came up with an approach using enriched finite elements, which I will give more details about in the future lecture, but I just wanted to highlight the fact that there are some very interesting work being done, because we think that astrocytes, I don't think anything because I'm not a biologist, but biologists think that astrocytes can be responsible for Parkinson's or Alzheimer's disease, because there would be different stages in the life of the astrocyte, and at some stage they could be retaining the food, let's say, for themselves, as opposed to giving the food to the neurons, which would further accelerate neurodegeneration. So this is something quite exciting. And finally, I would just like to tell you what I've been hinting at from the beginning, what these ideas of a digital twin are. So this is what we've been working on in many areas of research, from archaeology to space, through aerospace and biology and biomechanics. The idea of digital twin, which goes back to NASA, I think in 1950 or something like that, or maybe a bit later, I'm not sure, but the idea is really very simple. You have a real structure at the bottom left. This is, for example, a ship, and then you have information, data that's being acquired in that ship. So structural health, fractures, cracks, strain measurements, environmental conditions like temperature, pressure, and so on. And you want to use that data and assimilate it into a computer model. So this is the computer model that you have. This is basically a set of partial differential equations. And you would like to, or it could be agent-based, it could be many things. And you want to essentially live a parallel life to the real structure. So you have a virtual ship in here. And this thing is living a parallel life, and it is sending information to the real ship, giving, for example, inspection interval. Should the ship go back to port? Should it keep sailing? What is the crack growth rate? What are the scales of interest? Because depending on loading, it could be that one scale is useful or the other scale is useful. What are the workload combinations, and what are the best models that you can use to extract the parameters that you're interested in? So as you can see, there is a lot of information that can be gleaned. And of course, there is no reason why we would not do that with actual human beings, because we do a lot of medical tests during our life. And it would be very helpful if we could actually use these medical tests and give informed information to maybe the medic, or maybe to have a virtual medic that would be actually able to make decisions and help you make decisions, better decisions on your health, on your food, on your sports activity, on your social connections, on what you eat, what you drink, and so on, and what your gut health is about, and your brain health, and your dopamine level, and so on. So you could basically imagine anything. Of course, the devil is in the details, and there is a lot of work to be done for that to work. In particular, there is a problem of patient specificity, because all patients are different, but at the same time, you'd like to leverage information which is gathered through all the patients that you have. So you'd like to do some sort of updating of the information as you go. Okay, so that's basically where the whole my whole group is going, and I will now summarize it briefly in a few slides, which I think are very nice in order to understand what's going on. What are we trying to do? So there are, first of all, quite a number of cases in computational science, and as I think I made the case for, traditionally we've been dealing with experiments done on samples that were, gathered over tens of years, maybe hundreds of years, and tested. Now what's going on is a bit different, and this is what I want to show you here. Essentially, data-driven modeling is nothing else but we have a function or a functional that takes a point x and gives a point y. Right? So x can be a vector, of course, y can be a vector, and it usually is, and what you're trying to do is to find f. You try to find the link between the input and the output. Or you know f and you know x and you try to find y. That depends what the cases are. So what we've done until now is essentially, say for Paris law, we know the structure of f because people did a lot of experiments, and the parameters might not be known for this particular case that we are talking about. But still, we are dealing with model calibrations. For example, if you have a hyperelastic model of the brain or you have a poor elastic model of the brain, you would like to know what are the parameters involved with that that model, right? So you hope you know, because in general for a particular case, but maybe that the model you're using is able to capture case 1, but unable to capture case 2. That could very well be the case, because it depends on the quantity you're interested in. If you're interested in pore pressure inside the brain, of course, if you don't have a porous material model, you will never compute the pore pressure because it doesn't make sense in that model. So if you're interested in stresses, you may want to have a hyperelastic model that takes into account anisotropy, but if you're interested in displacement, maybe this anisotropy is not so useful. Or maybe it is, it depends on what you're interested in, okay? So essentially, sometimes the structure is known, but the parameters are not. And in the modern case, let's say, there is no a priori knowledge about f. So you just know nothing. You know only x and y. And therefore, your question is, how can I identify the model f? And that is the question. And that is what everybody has been working on and is trying to work on. So this is really the new paradigm is really included in here. And we had about, in the University of Luxembourg and colleagues, 35 to 40 PhD students working on this, maybe more, on trying to discover the model from input-output links. And so this is why we are working on all adaptive models. So model fusion, model selection, and how do we select the best model for the data that we have. I think this is something which is extremely exciting, and if I were in your place, I would definitely, as a young academic, consider working in that direction, because that is something which is universal, super helpful, and can really help in many areas. So a very simple example is urban wind energy harvesting. So if you look here at the Bahrain World Trade Center, it's basically put 3 of these wind turbines there. The problem is it's wasting 30% of the power on a daily basis because of a suboptimal positioning of the turbines. If they had put them in the other direction with the wind patterns, they would have made 30% more, apparently. I don't know this problem very well, but this is what it shows. So it's very nice direction. And the second one is trying to see what you can do with the usual methods. So, okay, that I will skip, but I will just tell you that if you, something that we could talk about also at some point, which is very well known by Hussein Rappel, who actually would be a very good lecturer for that, is that you have essentially you're trying to update your knowledge about the world as you learn. right? And I could give you an introduction on that as well if you're interested. So you have prior knowledge about something, for example, the parameters of the hyperelastic model of the brain, or of the power mechanical model of the brain, or the meniscus. You have some prior knowledge. You say coefficient A1 looks like a statistical distribution like this. Then you have data coming in and all other hypotheses that come in. And your idea then is to come up with a so-called posterior distribution. So you have a prior knowledge, you have data, they come into a Bayesian statistics module, and these hypotheses plus prior plus data give you an updated prior. And this updated prior goes back to the prior knowledge and becomes the new prior. So now you have the feedback loop, and that gives you a new prior. Of course, now you have a second little guy coming in, the office, or coming in with a new piece of material or a new patient, and you have this new data that you have here. This is going here, and then you multiply these two, and what you get is a new feedback, and now you get a new data. And so on, the third little guy comes in, and you get a new prior. And the fourth little guy comes in, and you get a new prior. And as you can see, the prior becomes thinner and thinner, meaning that you're more and more sure about what you will compute. So this is Bayesian inference. And for model updating and model parameterization is a very powerful feature that, that you should know about. Okay, so well, this is basically what we just said. About that first introduction, I would like to thank these funders and collaborators that helped us fund this research over the years. We obtained close to 30 million euros of funding for this since 2006, so it's quite a lot. And without that funding, nothing would have been possible. So now I will stop this presentation now because I think it's time, and maybe I take a few questions, and then we can move to part 2. So the idea now is to introduce a bit the basics behind what we call smart cloud methods, because I thought before I talk about material point method, which essentially is in the book that we just published with Nguyen Vinh Phu, that I'll give you a reference to, it would be nice also to tell you about some of the new things we've been doing on adaptive point collocation methods, so adaptive clouds, what we call smart clouds. And so I will first really relatively quickly motivate the problems that we're interested in, which are called free boundary problems. Because, well, free boundary problems are really everywhere in nature, and I want to give you some examples of that. Also because it's a problem close to my heart. I started working on that during my PhD, and I've not stopped since then. So this is, I think, very, very useful. And because I want to also give you a hint as to where I work, which is now here for 10 years at the University of Luxembourg, and this is where more or less where I live. In fact, you can see where I live on the hill at the right-hand side of the screen. This is where my house is located, and the university is this big L-shaped building, inverted L, or maybe you can think about it as a cross. And you see around it all the steel works. So it's really an interesting place. And there is, in fact, a sculpture which is done by an artist, which took part of, let's say, the sounds in China and moved them back to Luxembourg, because the idea is that one of these high furnaces to make steel was dismantled here and shipped to China and then rebuilt in China. And what they did is that they put some microphones and some recorders in the Chinese village where this was moved. And then they transferred the sounds to Luxembourg. So when you walk there, you can hear the sounds of the village, at least when the sculpture is working. And this is really a very nice connection, I think, that we have here. It's quite beautiful. And okay, so that's basically the campus. It's a super dynamic place, so I highly encourage you to try to visit me. There are lots of visiting programs. We could also think of China Scholarship Council, and I would be very happy to visit you as well in where you are, because it's very important for me to build this collaboration further. So this is also Luxembourg, it's the city center, down close to the river, very beautiful place. It's a medieval castle as well that you can see. This is the place, so it's in between France, Belgium, Germany, and it's very exciting because you have, for example, Schengen, which is where you get the visa from when you go to Europe. Well, this is close to here, and it is at the triple junction between three countries, which is quite unique to Luxembourg, and I think it gives it a very nice flavor, very international flavor. And if you compare, that's the Paris region where I'm from. This is called Île-de-France, which means France island. And it is 17,000 square kilometers, very small compared to China, obviously, and to any region in China. But if you look at Luxembourg, it's 2,500 square kilometers. So it's about 5 times to 6, or even 6 to 7 times less, 7 times less than the Paris region. So it gives you an idea what sort of scale these things are. Very small country, very dynamic. And you can see the team a long time ago. Now it looks quite different today, but still, it grew in size. We were at some point 35 people in the team. And so I'm very, very glad that you can see people from everywhere, you know, from Vietnam, you can see people from France, from Iran, from Italy, from Iran, from Dutch guy Lars, from Italy, again from Iran, from France, from Jordan, from UK, from Latvia, if I'm not mistaken, from India, from Greece, and from Mexico and Canada at the same time. So you see people from everywhere. Okay, so this is why Luxembourg is so exciting. I would definitely encourage you to come. I mean, again, I extend my invitation to you. Okay, so what are free boundary problems? So first of all, I want to give you 2 examples throughout the whole lecture. The first one is not wind turbines necessarily, but fracture mechanics, you know, stress analysis. Give me a component, I want to give you what the stresses are. Basically, that's the question. And of course, it could be applied to acoustics, it could be applied to any problem that you're interested in. And on the right-hand side, give me a brain that I want to cut. This is the brain when it's being, you know, open. And then the surgeon needs to do something about it, you know. So it tells you when you see that the complexity of the type of operations we're talking about, because if you don't know anything, how in the world are you going to do this, right? So, so what are free boundary problems? That is what we are interested in. So free boundary problems are solving partial differential equations, PDEs, in a domain, a part of whose boundary is unknown in advance, and that portion of the boundary is called the free boundary. And this was written by Avner Friedman in year 2000. So interface problems, they appear totally naturally. So why are we interested in interface problems? This is the name of my team, Legato. You know, this is a term in music. When you link up in Western music, you link the things up together. So this is different from staccato. So for example, if you sing la, 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 this is linked. If you sing la, 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 this is staccato. This is separated. All the 3 different notes are played differently, separately. So if you, again, I like these little diagrams with 2 dimensions. So you can see on the right hand, on the top, on the vertical axis, discontinuities. So as you go up, the discontinuities increase, and as you go right, the scale decreases. And the question is, what is going on? So if you look at an Airbus, or if you look at a car, if you look at the brain, then what you see is that these things are totally continuous. From far away, they look like one piece of material, like a potato. looks like one piece. It doesn't look like all the constituents. Obviously, if you zoom in the car, this is a project with Bosch, which was very interesting. I'll tell you about it if you'd like, on printed circuit boards and solder joints for my PhD student Alex Menk. Or if you look at the Airbus A380, you see all these very intricate layers of composites. Or if you look at the brain, if you zoom in, you always see that something is going on. So you see discontinuity. So if you keep zooming down, at some point things will become discontinuous. You will get to the atomistic level, and then things become continuous again because you're talking quantum mechanics. So you're talking about strain energy density functions. And you're talking about energy potential and so on. But of course, in the meantime, you have discontinuities to deal with. So this is what happens at the top here. You have this little solder joint. So the solder joint has 1 grain, 2 grains, 3, 4, 5, 6 grains here. It's very coarse solder joints. At the interface, you have a jump in strain. Why? Because you have a different material on the left and on the right. So these materials being different, you of course have different material properties and therefore a jump in the strain field. And you have a continuous stress, right? And you have a discontinuous displacement. Same here, if you have a continuous displacement because there is no crack, but here you have a crack, therefore you have a discontinuous displacement. So these discontinuities, they are very important. And I know that you guys are teaching XFEM, so you're very well aware of the importance of these discontinuities. Okay, so if you look here at the carbon fibers, you see a discontinuity across the carbon fiber and the matrix, and so on and so forth. So all these things are very well known. And now if you cut through a brain tissue, you will get a discontinuity here, which hopefully you don't need to mesh because it's easier not to mesh. So this is what we call free boundary problems. And again, if you go from the legato, where you sing all the notes in a linked way, in a very smooth way, different from staccato when you go at the small scale, when it sounds a bit like this with little jumps and discontinuities between the words, you see? So that's a different way to see things. So what we do basically is, this is a very nice concerto, which I really like, by Brahms. And if you think about what we are basically doing, we are orchestrating the sound of materials. If you go lower, you see staccato. If you go higher, you see a very smooth thing. So if you are listening to the material at the coarse scale, you would listen to something very smooth, but at the fine scale, you would hear very disrupted sounds with very many jumps. So there are many examples, multi-phase, you have fracture of concrete that you have here. You have here the problem of multiple bubbles that are created, non-Newtonian fluids here, and some sort of dam break example here. So lots and lots of different examples. Just after my PhD in 2015, I worked with Zhao and Dudu and Q on the problem of nanophase, let's say heterogeneities, where the problem was to find the optimal shape for these nano shapes, because they will optimize the energy density inside the domain and outside, as well as the surface energy, because we're talking about a nanomaterial, and the nanomaterial happens to have a very high energy on the surface, which is why you don't get a sphere as an optimal shape, but a shape which will also take into account the length of the interface, not only its surface area. Another example we're interested in is the keloid, which is a scar between healthy skin and non-healthy skin, which is a keloid scar. Very similar to cancer in many ways due to inflammation, we believe, and we have experiments going on with biologists at the moment trying to figure out how these keloids grow and why. But as you can see, there is an interface between the keloid and the healthy skin, and it grows over time. This is another example of what we are interested in. And we have a weak discontinuity. Another example, so the key point here is to try to figure out what is the growth of this biofilm. So on the interface, you will have a velocity potential, and that will have a gradient, and this gradient is going to push the material outwards, for example, right? So this is going to be the bacteria growing and pushing outward. And so outside in the water phase, we have a Laplace equation, and we have a Poisson equation in the bacteria phase, right? Okay, so now the problem is, when do free boundary problems occur? So, of course, fracture mechanics, Taiwan earthquake, fragmentation of concrete, landslides in Colorado, lots of examples of fracture, like the Comet aircraft, which became a convertible aircraft, but that was not foreseen. A problem of fracture in biomechanics, and so on and so forth. So fracture is really everywhere, and what I show today are simple examples of what you can get free boundary problems with. For example, here, needle insertion inside the liver to try to deliver a seed to a cancerous tumor. And here you have solder joints. In the middle, you have fracture of a concrete beam, and here at the bottom left you have a smart cut phenomenon with hundreds of cracks growing using XFEM. This is the work of Dana Sutula, which is really amazing work, and work with Lisa Cahill in Limerick at the bottom right, where you see the propagation of cracks in composite materials. So and of course the work of Xuan Peng, who did his PhD with me, and Elena Troshenko on propagation of cracks using isogeometric analysis with boundary elements, which is one of the best work that we've ever done, I think. Okay, so now, first example, cracks propagating inside a domain. So you would like really to figure out what exactly is going to happen, what is the most energetically favorable growth of crack that we can do in one increment. So, you know, you do a global minimization on all the crack tips, and you try to compute which crack should grow. And as you can see, it starts here, but then at some point, the most optimal crack is not here anymore. It starts to grow next to it, and so on and so forth. It's a very complex problem to solve, and Dennis did that in very simple MATLAB code. Well, not so simple, but very beautiful work that he did. Again, cutting in soft tissue that I've already talked about today. And the discretization. So now what is it about discretizing moving boundary problems, and why maybe do we need mesh-free methods or collocation methods or similar? So first of all, what we can see at the top is what happens in finite elements. So in finite elements, you have these interfaces that grow, right? And these interfaces maybe merge together. But as you can see on that picture, the mesh is conforming to the interface. So you see the mesh is always following the interface. So this is called conforming meshing. On the right-hand side, you see a crack, and the crack is moving with this little roses around there, which is fixed, but moves itself is fixed, but is being attached to the surrounding mesh. So this is beautiful, but it's also very costly, in particular in terms of remeshing. And it's sometimes almost impossible to remesh in 3 dimensions with all these cracks propagating and coalescing. You can imagine the complexity, because you get very small elements, and generating these meshes is not feasible in finite time in general. So we cannot know. So that's why people came up with partition of unity methods. The book that we released, we will release in October with Sundar in IIT Madras. And what we see there is that the mesh is independent from the growth of the interfaces, because we can include discontinuities and singularities in the approximation field. So that's been quite a big advance in the last century. So now there are really 2 approaches to handle interfaces. The first approach is use, let's say, a coupled approach. So what you want to do is you want to couple the mesh with the geometry. That's step 1. What you want to do as a second approach is the opposite. You want to decouple the mesh from the geometry. And that is quite interesting because at the end of the day, it seems like you have two approaches that are opposite to each other to solve the same types of problems. You see? So now, how does that work practically? Because you would say, in one sense, that you would like to keep the same representation from the geometry and for the simulation, so that would be something like isogeometric analysis. On the other side, you want to decouple, so you want to have the mesh which is independent from the geometry. So these two approaches seem to be totally opposite. So what we're going to try to address today and now is, what are the better approaches? What is the better approach? Of course, there is no general answer to that question, because if there was a general answer, there will be no research. And when should we go for one and when should we go for the other? And what is the role that finite differences can play, meaning collocation methods? Collocation methods are not hugely popular, except for boundary elements maybe, but in terms of more general collocation schemes, they are really secondary approaches. So we try to rejuvenate them, and we wrote a few papers on the tutorials for these topics. If you're interested, I can give you the list. In fact, it was in the bio that I sent earlier. Okay, so now let's see what we can do. So now, there are two approaches. Let's see what generalized finite difference methods can do. So what are these generalized finite difference methods? So if you go back to the literature, you see 1953 already and 1960 with McNeil, Forsyth, and then Frey 1978, Jensen 1972. And the idea is really to use Taylor series expansion to obtain finite differences. And using that, you try to approach the derivatives of the operator, right? So you have an operator, it has first, second, third derivatives in time, space, you have Laplacian, you have different operators, and you want to look at these operators in terms of their numerical formulation. And you want to approximate the operator, different from finite elements, where you want to approximate the field, the unknown field. It's quite a different idea. In one case, finite differences, you approximate the operator. In the other case, you approximate the unknown field. Very different problem. At the end of the day, it boils down to the same solution in one dimension. You get the same equations, but the approaches are totally opposite to each other originally. And the idea is, how can we can easily imagine calculating a derivative by looking on the right, looking on the left, doing the difference, and divided by the length of the interval. That would be an approximate of the derivative. So, of course, this is possible, but now let's imagine that you are in 2 dimensions and that the points are totally irregularly placed, maybe using a finite element mesh. Then how do you do it? So this is called generalized finite differences, and there are some papers that work on this. And the question is, how do you compute the operators? And that's what we will see in a few slides. Now, why really use strong form methods? Because these types of methods are known as strong form because you immediately, directly write the partial differential equation you're interested in at all the points in the domain that you want to solve it at. So you say, I have Laplacian plus b equals 0 here. So I compute the Laplacian locally. It gives me an operator. I put that on a row of the matrix. I compute b of u. I put that on the right-hand side. And that gives me the operator I need. That's it. So this is quite straightforward in general, at least for linear problems. Now, what about the approaches that you can use in order to write these operators? right? So this is really there are different questions. So for example, you could use radial basis functions. So in that case, what you do is you say that, okay, you assume that you have a cloud of points, and they are used as a basis to build radial basis functions. And these radial basis functions are then used to compute the derivatives in question, right? So what you say is a bit like a Galerkin method. You substitute the radial basis functions, and then you use the Kronecker delta property to end up with the equations at each node. Right? That's an approach. Okay, and then there are some mathematical results about this, but needless to say that having a mathematical approach to point collocation methods is extremely difficult. So there are different approaches. The first one is to have a finite difference stencil on irregular centers and to use polynomial least squares method, for example, Benito. And this is known as local collocation. Second is you use radial basis functions, which seems to be better for irregular data than local polynomial least squares, right? With, of course, some disadvantages of RBF. Then generalized finite different methods will allow a lot of flexibility in the choice of stencil supports. Although RBF and GFD are not developed as much as the polynomial methods, of course, because polynomial methods are very easy to use, you can build polynomials very straightforwardly. Okay, so that's basically that. And then about RBF interpolation, you have different choices for that. So you have conditionally positive definite functions, multi-quadratic inverse multi-quadrics, Gaussian Wendland C6, and so on. So there is always a trade-off between the accuracy of the interpolant and the scaling parameter, because you would like to have small scaling parameters so that you can remove, the large bandwidth of the system matrix, but you also would like to have smooth solutions that are stable. So you would like to have a scaling parameter which is as large as possible, but still have a numerically non-singular RBF matrix, and that is the art. And I highly recommend that you read the papers by Davidov, D-A-V-Y-D-O-V, sorry, because he is one of the world leaders in that area. And recently with Pratik Suchde from my team, they wrote a review paper on how to place the centers of collocation methods in general and how to optimize the point placement. And this review, I think, is outstanding. So I highly recommend it, as well as the work of my PhD student that I will show you later. Okay, so what are collocation nodes? So we have collocation nodes are here. So, okay, that's one point, XC. You have a radius, RC, and you have a field point, XP, that are also known as particles. And the support is this area over which, or the volume over which, the point XC has an influence. And so the question is, okay, what would you like to do? Well, you want to compute the derivatives at XC, which can allow you to reproduce the field values at each particle pi of the collocation node support. Okay, so basically you want to compute all the field derivatives here, which allow you to compute the values at points pi. Okay. So what is a finite difference method? Well, that's what we said before. All we do is we write at xp at any point, right? That is here. We write the value as the value at xc plus some corrections that come from Taylor series expansion. What else can we do? I mean, it's the very logical thing to do. If you assume the solution is smooth, very important point, then you can do that very easily, and there will be some convergence radius of the Taylor series expansion and so on. So you know that you will eventually converge if the solution is smooth, and only if it's smooth. If you have a very strong gradient, then the collocation method from that standpoint will not work, because you have a Taylor series expansion, which is a polynomial function trying to approximate a jump or a singular value a singular function, and of course we know that doesn't work, and you are facing with the problem of Gibbs phenomenon. So this is not what you should do. Okay, so now let's imagine that you use a second order approximation. If you use a second order approximation, you'll see that you have first derivative with respect to x and then y, second with respect to x, second with respect to x and y, and second with respect to y. If f is smooth enough, this one is the same as dy dx, so there is no issue there. Now what we can do is for a support composed of 5 particles, so remember what the particles are, they are here, so let's say 1, 2, 3, 4, 5. We have 5 particles in the support. We can write 5 equations. XC, C is the center, it's the collocation point that you're interested in, so you just write the Taylor series expansion for each and every derivative that you're interested in. Okay, so then if you do that, you write this times this, plus that times that, plus this times that, and so on, will be equal to f of x p1 minus f of xc. So what you essentially do is for each of the points, p1, p2, p3, p4, p5, you write the Taylor series expansion, which gives you f of x p1 equals f of xc plus the corrections due to the derivatives, and you do likewise for all the other points. So now you can see that if you have 5 particles, you can write 5 Taylor series expansion, and therefore you can hope to find 5 values for these derivatives, because that's what you're looking for. After all, what your question is here is what is the derivative of function f at point xc, what is the with respect to x, then with respect to y, with respect to x twice, and then x and then y twice. And so that way you have an approximation of this. So this is what you do. You put that in matrix form. You invert the matrix. You hope that it's invertible. Of course, that would be hopeful. And that's what you get. So now the problem is that in the previous case we had exactly 5 derivatives and exactly 5 points, but that will never happen. I mean, usually you will have cases where you either have too few points, in which case you can't do anything, or too many points, in which case you can do something, but the system is overdetermined. And of course you cannot solve it exactly, but you can solve it in the least squares sense, which essentially boils down to doing it this way. So now what you do is you have a least squares functional that you're writing, and you try to minimize that with respect to the parameters. Okay, so so far so good. That's the very usual way of doing things. Now there is a second approach which is maybe unfortunately not very well known, and which is known as the discretization corrected particle strength exchange. So I have to say that the first time I heard this, I thought that was a mouthful, because it's quite complex to even read, needless to say, to understand, but there is a lot in that method, and I will try to tell you a bit about it, because I'm almost sure that you probably didn't hear about it. And if you like, I can also give you the papers, because they, I think, are quite useful. So let me start from the beginning. So what we do here is that it's exactly the same as before. So we try to identify the value of the derivatives at a point xc. So it would be like that one. We try to get the fh, the x. We try to get, of course, the value of the function, the first derivative with respect to x, with respect to y, partial x, partial x, partial x, partial x, partial y, sorry, there's a typo here, and partial y, partial y. All right. Okay, so now what we do is we write it now as some sort of integral, right? Instead of writing it as a simple sum. So then we end up with some sort of, let's say, moment matrix, Mij, and that moment matrix we use directly in order to identify or to compute the coefficients that we need. Okay, so basically we did exactly the same as before, except that we are now correcting with an integral value, right? So this is the basic idea. And on that topic, I recommend that you look at the work of Ivo Balzarini at Max Planck Institute in Dresden, because he is one of the world leaders in that area. He came up with the idea with his PhD supervisor, and he's really an excellent guy. Okay, so once we have selected the appropriate function, because basically we have a smoothing function, which is this kernel here, we can apply the desired derivative, and we just set all the moments to 0 except the one that we are interested in, which we set to 1, and we do that alternatively. So first we set the first moment to 1 and the others to 0, and then we set all the other, the first to 0, the second to 1, and all the others to 0, and so on. And that gives us essentially a set of equations which we can solve. But first we need to have a weight. So again, like in mesh-free methods, we have exponential weights, third-order spline weights, or fourth-order spline weights. We can use different things, and of course they all have their own advantages and drawbacks, which I identified in the papers as well. And that's it. So now we are going to look at a few problems using this discrete correction particle strength exchange. Just to let you know, what we have managed to do is to have an adaptive point collocation method. So this adaptivity allows us to optimize the point placement based on an error indicator. Okay, so similar to what I was telling you, if you remember, about the surgical simulator, when we were trying to identify what would be the best mesh for the system, this is something that we are interested in here as well. We would like to have the optimal point distribution in that case. And I'm really encouraging you to look at the papers that I will give you, because they will allow you to understand better the way we do it practically. So the first thing we remark by solving the problem, so here we're solving a very simple linear elastic problem with internal pressure in a sphere. Well, you know what I mean. So basically we're doing that, and we're computing the stresses, and we're doing that on a code which is parallel, and that's also available if you're interested. And we are looking at different values of the weighting function. So either third order, fourth order, or a linear function. So what we see, linear function, the error on sigma 1,1 is constant, and we cannot decrease it by changing the power parameter. But in the other cases, we can see, in particular for the fourth order spline, that we're getting better results than the others. So this is what we therefore used. And the thing is that depending on each case, that was generalized finite differences. And now for DCPSE, well, you see that you have some sort of optimal shape parameter, which is given here, which will give you the minimum error. And then if you increase it too much, the error increases again. And if you choose it too small, the error increases again. And you see that this optimal parameter is about 0.3 to 0.4, at least for this particular case. Again, if we compare polynomial basis to exponential basis, what we see is that we have much better results with the polynomial basis, up to 1 order of magnitude less, even 2 orders of magnitude less error, which is great. So it's basically, it's the opposite. Polynomial basis better than the exponential basis. And we still don't know why, but that's what we see. Now, if we look at the support size on the boundary, because this is a very important question, what happens close to the boundary? In mesh-free methods in general, a lot of people are avoiding the problem, But you know, even in Galerkin mesh methods, you have this support that intersects the boundary, and when that happens, you lose the Kronecker delta property on the boundary, because you basically lose everything in terms of you do not have a zero test function on the boundary anymore. So this is something that we need to take into account. Okay, so that's that. Okay, so now what can we do with that? So let's look both at Voronoi diagram GFD, so where we have generalized finite differences, and the points in the generalized finite difference are distributed using a Voronoi diagram, which is a very well-known and approach, which is dual to Delaunay triangulation, tessellation. If you have more nodes than derivatives, you need a least squares approach, and the contribution of each node in the fit only depends on the distance between the reference node and the support node. And the Voronoi diagram can be used to add geometrical information, right? So in DCPSE, if more nodes than derivatives, there is a least squares approach, and the contribution of each node is in the LS fit only depends on the distance between the reference node and the support node, and the Voronoi diagram can be used. But we use a convolution, an integral, discrete sum, weighted by area, and not simply unity. So this is what DCPSE changes. So let's look at how it looks. This is a Voronoi diagram, reference node and support node. So if we use a Voronoi weight as opposed to a simple weight, we see, well, basically that there is almost no difference. So this is reassuring, so which means that there is probably no need to be doing these changes. Okay, and now those are the results with mesh convergence, which is a hard topic because there is no proof of convergence for such methods, so we can only hope to get things as beautiful as finite elements. Let's look at efficiency. So we have different methods here, and we try to look at the convergence rate in terms of the L2 weighted average. And the convergence rate actually is not that bad, because it's actually close to what we would expect in finite elements, which would be 2. But here, for that problem at least, so you see that in terms of the time to compute, there are different methods that we tested: interpolation, MLS, RBF, FD, DCPSE2, and GFD. What we see is that clearly the convergence rate that we get, which is one of the best, is DCPSE2, and we get a computational time which is significantly less than IMLS, which actually is half. It's better than generalized finite differences, so clearly it seems like DCPSE is the method to choose. And yeah, so now if we let's look at some conclusions. So first of all, we need a sufficiently large support, but also not a too large support, because otherwise we end up with a huge bandwidth, and this is not stable. Well, and this is also time consuming in terms of memory. What we see is that we need 11 to 15 nodes for 2D problems and 37 to 45 nodes for 3D cases. And we need, let's say, a large number of nodes to get proper simulation. Okay, and what does it mean in practice? So if we look at this flange here, we assume there is uniform pressure loading here, displacement constraints there, here, and there. And now the question is, what is the deformation of this? Again, we started directly from a CAD file, so from NURBS, which was discretized using 2 approaches. So one was an STL file, which is basically a triangulation of the surface, and the other was simply putting collocation points along the splines using the splines directly without any mesh. And I think that's also very, very nice. And the third was to embed the whole flange into a regular lattice of points, so that we don't even need to know where the points are. And we just then add the points on the boundary as needed. I will talk about it a bit later. Okay, so now we look at the results using generalized finite differences, that they look like that with a very nice stress concentration. And now I'm telling you what we are working on. So although now most of the results are in the recently published papers that I was mentioning. So let's imagine that you have a structure to look at. So for example, this little bunny. This little bunny is, of course, relatively a simple shape in that case, but it could be, of course, a much more general shape. And the idea would be, okay, can we simply have a general regular mesh, and can we put some points which are either in or out, and then work on imposing boundary conditions. So first we impose the Dirichlet boundary, then we impose the Neumann boundary, if you can see the points that are here at the interfaces, intersection points that I just created. Then we impose maybe the Neumann condition, so we need some more points along that surface, which is known maybe by NURBS. And what we are now able to do is to do all this for very generic problems. Of course, you will have some regions where you have problems. So for example, here you can see that you have a cusp inside this element. So of course, you will not even see the difference here. You will have only one material inside that box, and you will not be able to solve it. So what you, of course, can do in these problematic regions is zoom in. And once you have zoomed in that region, you will simply add points at the interfaces, at the intersection between the geometry and the mesh. And that's it, basically. Then that will allow you to have a better description of the boundary. And we do that in a semi-automatic way, let's say. So same here, we will have to add some points which will allow us to take care of the boundary. Now we don't have of course we are not able to handle a kink, because that will create stress concentrations, and we can expect that we need here some more points. And again, the paper by Pratik Sushde and Oleg Davidov is talking about this very nicely. Okay, so now there are some references, in particular from Davidov and Hoan and others, that are very, very useful. Some references by Benito on how to compute DCPSE. So I can give you those references as well as the presentations if you are interested. I think it's very worthwhile reading this. In particular, that paper with Oan and Davidov, because that will give you quite a number of ideas. So what we do is, from an STL file, we embed the STL file inside the domain. We cut everything that's outside, and we look at the convergence. So here we look at energy, Cartesian, symmetric, and so on. So we look at all the different convergence rates, and you see essentially the results is that the convergence is in the L2 norm of slope 1, which is what you would get. So you would expect 2 in the L2 norm, and you get 1. As you would expect 2 in finite elements, so here you get 1, right? So this is something that you need to take into account, right? Again, if we use different approaches, we see the convergence rate on that curve. Okay. So in terms of number of nodes, we can compete with finite elements. So you see finite elements here, collocation here. So in fact, the slope is a bit smaller, but not much. And for the Cartesian case, we get a higher error, but the slope is approximately the same too. Then we dealt with these very nice problems of a chair. Again, this is done with open source codes like open source Elmer, Codaster, and FreeCAD. And we have different materials here, and we have different nodes and tetrahedral elements and so on. So it looks like that. You have about 1 million elements. And we are comparing all three solutions between what we're doing and the different solutions. So yeah, if you look at the cut view of the distribution on the seat, you see that there is barely any difference. If you compute the von Mises stresses, you see that there is quite a good distribution. And yeah, and finally you see this. This is basically a wind turbine blade that we were working on, and we definitely need adaptivity, and this is something that I would really like to talk about, because this is a problem which is, first of all, close to my heart, because I've been working on it like for really ages. And I think adaptivity, in fact, I will show you the paper later if you are interested, but essentially adaptivity will allow you to, let's say, optimize the mesh and the point placement given an error level. And again, here we always assume that we do know that the problem that we are solving is the right problem. So we're not asking the question, is it the right problem? We're just saying, this is the right problem. Are we solving it right? Are we solving it precisely enough? Okay? So that's really our main challenge. And so how do we deal with error estimation? And I will come back to that at some other time this week. I just want to tell you for now that we have worked on that with a company which is a research center called Senairo, and they have implemented this in their commercial version for 3D fracture mechanics. So you see how a crack can propagate, and it's actually decimating the number of points. So we have far fewer points for the same error. Because what we were interested in here was to minimize the error on the stress intensity factors. Because the stress intensity factor is, if you remember from Paris law, the governing point with which you are solving the propagation of the cracks. So if the stress intensity factor is inaccurate, then what you get is an inaccurate propagation growth. So it's very important to have proper stress intensity factors, right? So now, how do we deal with that? If you look at the number of elements close to the crack front, you see that it's quite dense, and you would not like to have such a dense mesh everywhere, because that would be totally unfeasible. So that's what we did. Similar for surgical simulation, you want to insert a needle in a brain, if you do, or in a liver, wherever. You have localization here, clearly. You have high stresses, shear stresses and shear strains until the needle penetrates the organ and reaches the target, right? So what we did is we developed a real-time error estimate, which is able to compute in real time the approximation error, which means the ability of the numerical simulation to capture the exact solution, well, which we don't know. So this is a bit of a mathematical miracle that without knowing the exact solution, we're still able to give an approximation of what the error is. So this is something quite amazing. So we insert the needle in this virtual liver. This is work by Bui-Phuoc, and then you see the needle is inserted, the mesh is refined, and as we retract the needle, the mesh is then unrefined, because the stresses are not varying that much anymore, right? So we insert the needle, puncture, the elements are refined along the needle path according to an error estimate. It is not random refinement, as you can see also here with the boundary conditions. There is some local refinement because of error levels. Then we retract the needle and the mesh is coming back to its original density. Okay, so that's how it looks if you insert in a brain the cannula, which is used to insert an electrode and reach a target to stimulate with an electric current pulse the target for Parkinson's, let's say, not treatment, but alleviation of difficulties. And so yeah, that's it. And now I will show you the list of papers that we published on that topic so that you can take a better look. And I think I will end with some basics about the material point method, because I think it would be more suitable. And then in the coming days, I will be able to tell you more about the topics that we talked about today that are, in my opinion, quite important. And of course, in the meantime, feel free to tell me what you would like to talk about, and I will do my best to make it happen. Okay, so this work is mainly done, so this is a mesh-free work. I've introduced you a bit about, mesh-free methods. We have talked mainly about point collocation methods, but you can also think about mesh-free methods as Galerkin methods. I think one of the very well-explained topics on that area is by Atlouri, who unfortunately passed away. But we have basically the MLPG method, so moving list Petrov-Galerkin. So MLPG is a really, really nice way to think about all mesh-free methods. And if you like, I can also give you a categorization of all these methods, because they can all be formulated within one overarching framework. So the material point method, this is work done mainly by Nguyen Vinh Phu, who is in Monash University. We wrote together this book on the material point method with Alban de Beaucorbeil, so a colleague of Phu. And I just want to motivate a bit what these methods are able to do, because what's really quite interesting is that they are quite related to what we use for the meniscus problem that I showed you earlier today. So Alban is the guy that I was telling you about, who worked with Phu. He's in Deakin University. Sina in Melbourne. And Tushar Mandal, who was a PhD candidate with Phu. And this was funded by the Australian government and Australian Research Council for Phu. Okay, so what you see here is deformation, fracture of solids. So this is a totally different type of problem than what we've talked about until now, in the sense that you have very large deformations and fragmentation. So it's not really a problem with large deformation is usually quite tractable, but certain problems are, sorry. Okay, certain problems with fragmentation are much more tedious to address than problems related to large deformations, because fragmentation means that you have several subcomponents of the solid, and this is something which can cause quite a lot of issues. Okay, so for example, if you imagine this cube that enters this other cube, this is, for example, a bullet entering a domain or a piece of armor, then you can see that this region is extremely stiff and that one here is much more soft. And the question is, what would be the number of fragments that you end up with? What would be the energy absorbed? Or what would be the velocity of the outgoing component? So that piece that is being thrown out. And that's important for obvious reasons in terms of engineering. And so if you were to solve that using finite elements, the problem would be really quite intractable. And I'm saying this because the idea of mesh-free methods dates back to Monaghan. So I hope you still hear me because there were some issues. So the problem of mesh-free methods is clearly dates back to Monaghan, 1975-76, and originally that was really the SPH method. So if you look historically, you start from the smooth particle hydrodynamics, which was written in a quite simple way at the time. Then mathematicians and engineers figured out that there was some instability to this method, tensile instability, and they tried to address it, and many versions of SPH were produced. Okay, so I think that's essentially the main point. And after that, there were some different types of mesh-free methods that came about. And I could give you an overview at some point about the history. It's also given very clearly in our Partition of Unity book that will come out in October with Sundar. But if you are interested, I can give you a very quick overview. Essentially what happens is that in 1994, just at the same time as the Partition of Unity comes about with Melenc and Babushka, who unfortunately also passed away recently. With Melenc and Babushka, we get this idea of partition of unity, which I will define in detail in a forthcoming course. But the thing is, with the new mesh-free methods of the time, is that they try to address problems related to smoothness of the solution. Right? So the idea is to try to come up with solutions which are smoother, that are, for example, C1 for shell elements, for example, or that have high local reproducibility conditions so that you can reproduce very smooth functions. Or you can also think of cases where you have local enrichment, right? And there are then different topics. There is a notion of intrinsic enrichment and extrinsic enrichment, which I will define in detail in some forthcoming lecture. But suffice it to say now that there were original ideas for mesh-free methods were to handle problems such as the one you just saw here, which is fragmentation, delamination, or explosions, where you start with one piece and you end up with a large number of pieces at the end of the simulation. So you have one domain splitting into subdomains. And then the notions of mesh-free methods such as elementary Galerkin with Belichko 1994, who also passed away in 2011, as well as the work by Oden, who also passed away this year. This is really a sad year, where he worked on HP clouds and similar methods with Duarte and generalized finite elements. All these methods are based on trying to enrich the approximation. So the idea of mesh-free methods in that context is no longer to try to deal with fragmentation and things that split up into pieces, but it's really to have a solution which is high-order continuous, enabling things like shell problems, shell elements, or maybe fracture problems if you want to have higher flexibility in the way that you write the approximation scheme. So that you can reproduce any function. I will come back to that. So basically that's the idea of what you want to do with MPM. So MPM is some version of of SPH, which is much more flexible because it both relies on a mesh and on a set of particles. So typical applications. So you see that thing here is like a tube which is undergoing an explosion, right? So if you have a tube that is under pressure, for example, with gas or some sort of explosive, and you look at the fracture mode, this is clearly an elastoplastic fracture mode, and you have clear plastic deformations in this tube. And the question is, how do you manage to simulate this, right? So this is the problem. Similarly, you may want to solve a problem of flow around a sphere in a domain, and that would be something that you could do using particle methods, and these methods are also the ones that we use with DCPSE, with anisobedat, in the work that we are doing on the meniscus. So, okay, I hope that this gives you an idea what the basic ideas are behind the application areas. Okay, so what do we typically do? Well, we typically write the balance equations, so constitutive models, or kinetics, and so on. And we have some geometry, so in that case, this little tube that probably connects to valves. Then we get some equations for that. Very simply, we code in a computer, like, finite differences or whatever we solve, and then we get a result, right? So in that case, a fragmentation of a piece of something with a bullet or something similar. Okay, so now what are mesh-based and mesh-free methods? Of course, here we're talking, very briefly. Mesh-based, we have a mesh, obviously, by definition. However, it's not so easy in the literature, and that's why we wrote this paper in 2008 with Fu to try to make things clear, because the literature, when I was doing my postdoc on mesh-free methods, was very unclear, and that's how I really figured out how things worked and what was really important. By writing this paper, it was extremely helpful. Also something for young academics. If you ever find a topic which you don't understand, the best thing to do is to write a paper about it, because once you've written the paper about it, you will be for sure really knowledgeable about it. But if you do it properly and you try to make everything crystal clear to the user and the reader, as we did in this 2008 paper, which is now cited, I think, over 1,000 times, I think you will see that this is highly helpful. And also you can think of giving the codes away, because that helps people build confidence and also learn faster. So, okay, what is a mesh, basically? That's the question. So a mesh does many things, and that's why when people talk about mesh-free methods, it is so ill-defined, because a mesh has many, many roles. The first role is to build the approximation. You see here, you have these little nodes, J, and a point, psi G. And what happens with that? Well, I mean, the nodes that you have here are used to build an approximation scheme. So they are used to build what are called shape functions. They are called shape functions because we are usually in an isoparametric element formulation, and in that case, they represent essentially the geometry as well of the element. So, we have polynomial elements, polynomial functions, and so on. So we can just simply do that and compute, and we have now a shape function everywhere which is used to interpolate inside the element. Second role. So what is the second role of a mesh? Why do we need a mesh? Well, usually we use a mesh because we need integration points, like psi G here, right? So what are those things? There are points that you use to integrate the weak form, because you have a weak form. Contrary to what I just presented about point collocation, you have now a weak form, and the weak form needs to be integrated somewhere or other. And we use the Gauss points to do that. Then finally, it's used for post-processing, because we use the Gauss points to post-process. And it's used to represent the geometry of the domain, because without the mesh, we clearly would not be able to represent the geometry. So that's basically what it does. Of course, you have many mesh-based methods, such as finite volume methods, FEM, and even in a way, finite difference methods can be seen as a mesh, except that there is no connectivity per se. The connectivity is not fixed like in finite elements, it's variable connectivity. So not only is it efficient and accurate, but it also has sound mathematical basis. But it has some problems which are related to mesh distortion. So if you really take this element that you see here and squish it completely to make it a line with all 4 nodes aligned, the transformation between this element and the parent element will become ill-posed. So you will get a negative Jacobian, which will create huge problems because you will get negative terms in the stiffness matrix, and this is not something you like on the diagonal, of course, because you want a positive definite stiffness matrix. So that would not be nice, and there are many ways to go around that. For example, strain smoothing stabilization. This is something that, if you are interested, I can talk about. Or mesh-free methods, which are less sensitive to distortion of the mesh. I say less sensitive because my own experience of moving least squares, elementary Galerkin, for example, is that it is quite sensitive, actually, to point placement. And this is also what we see in finite difference methods, where if we have suboptimal point placement, things go quite bad, I have to say. Okay. Meaning that we can get results that are completely wrong, right? I mean, at least not convergent. So in mesh-free methods, you have points or particles. Example, EFG, as I said, SPH, which is the first one, PFEM, MPM, material point method, and so on. And in that case, the goal is that you are not subject to mesh distortion. Again, this is not so true for EFG, for example, or any method based on moving least squares. My experience is that it is quite sensitive to distortion. And the other problem is that the geometry is not necessarily very accurate because we have only points and we don't know what happens between the points. So we cannot get very detailed cases. Okay, so now what is the material point method? So first of all, you have to know about Solsky because she is the one who came up with the idea. So you can, of course, take a look at what she wrote, and you can also take a look at our latest book. I'll give you a reference. And if you can get it, I think it will be useful reading. Okay, so you have grid nodes, which are here, right? And you have particles. So these particles are superimposed onto the grid nodes, right? So this is something like a mixture between finite elements and particle methods or mesh-free methods. Okay, why? Because you have the structure of a mesh, which you will see is used to exchange information between particles. And you have the flexibility of having these particles present in the domain. So you have both, and that is something which is highly desirable. Okay, so now what is included in the particles? You have the position, the volume, the momenta, the stress, the temperature. So all the field variables basically are stored. This is what you are interested in. So there are, of course, many variants of the material point methods, as you can imagine. And the idea is the following. You start with a set of nodes, which are regularly distributed, and you have a set of particles, which are randomly or irregularly distributed, and you exchange information through the nodes. So the nodes that are here, fixed, will have some way of learning from the particles what the values should be. Of course, by interpolation or extrapolation. So that's point to grid. All right, so now if we have some sort of distortion of the mesh, then we can recompute the values at the grid, and we can update the grid. And then what happens is that the particles move around, and we need now to go from the grid to the particles, right? Because you see very clearly here that now we have a new grid, right, which moved around thanks to the knowledge of the variables known at the points level. So we have the points, particles to grid. Now we have the data here, we can move the grid. Okay, now that we have the grid, we can project back to the particles, grid to particles, and the particles can then move forward, and we reset the grid back to its original position, and we keep going. So the grid is basically there to help pass information in a more stable way from particles to particles. So it's like an approximation scheme. And so MPM is really a very cool method because you can deal with really super complex cases. For example, here, large deformations, you see these little beads here, they are actually simulated, right? And you can look at how they deform. It is a really super method. You can look at the Taylor bar example as well, and at these problems of penetration. Similarly, you see here the type of very, very difficult problems that that you can address, of really crushing of a foam. This is absolutely, this is a very, very difficult problem with self-contact. There is a self-contact here at the interfaces. These problems are really difficult to solve. This is not something that you do with finite elements in any simple way. But you see here that the problem is solved fast, let's say, and accurately. And this is done by image-based analysis with huge deformations, really enormous, with self-contact. Then explosions, and fragmentation is something that you can do. So this is very nice. This is called hypervelocity impact with Johnson-Cook model. Really huge simulations with Caramello. There is no mesh generation, very simple basis functions, very large deformations, automatic no-slip contact, also multiple contacts can be done, and simple boundary condition treatment, simple implementation. So, but there are some issues which I don't know if we'll have time to talk about today, but at least I will talk about the issues, but not about how to resolve them, because we have 11 minutes left, I think. So it would be better to have some questions and discussion. So what are the issues? And they are very similar to what I was talking about in SPH at the beginning. So if you look at these two annula that are colliding, so what is that? Clearly that's not something that you want, because this is not a structural effect at all, so we'd like to get rid of this. And this is called cell crossing instability. So let's look at what that means. So in total Lagrangian, you have the balls that fall, and everything comes back to the original configuration. And in the standard way, you see that you don't have that. You have direct separation between the two, right? And so this is what you actually do not want, right? So you have here this virtual crack, which should not happen. So this is known as numerical fracture, and this is very, very well known in SPH because it was known as tensile instabilities. And well, I think I will not go into these details now, because otherwise it would probably take another half hour, and we don't have this half hour now. I think I would rather go back to you and ask if you have maybe questions, which would be really nice. And then, yeah, I'm looking forward to hearing ideas about what we could talk about next time as well.